Okay, guys, so how do we compare to theory? How do we compare our experimental result to the theoretical equation and make some analysis for how good or bad your results are? The first thing to do is to actually write down what your theoretical equation is. So what we've got here from my results is D is equal to, so I'll write that out now, D is equal to 0.28 t squared minus 0.0482. You have to make a comparison of that equation to your theory. Can someone tell me what is the theoretical equation? And where do you find it? Anyone know? Yeah, well, it's part of it. Now, in the beginning of every practical investigation you get for this internal, you'll be given the theoretical equation, and it's normally at the very beginning of the brief. So if we go back to the actual experiment over here and have a scroll through, you'll actually find, if we look hard enough right there, I've highlighted it, that there's actually the theoretical equation that's given to you. Okay, so I'm going to write that down underneath my equation, and we're going to make some comparisons. So we have, in theory, we've been told that D is VIT plus a half AT squared, and they tell us that A is equal to G sine theta. So that is our theoretical equation, and we have to go through a process where we can compare the two of them and see how good our one is. All right, let's try and simplify the theoretical equation to make our lives a bit easier. Can someone tell me what is the VI in this experiment? Initial velocity, which is 0. So we can pretty much eliminate the VI times t part, because VI 0 times t is 0. So we're going to have here just a half AT squared. Of course, we still know that G is A sine theta, so we can actually go and say, well, in that case, D would be a half. Instead of writing A, we can write G sine theta, and we have our t squared. So all I've done there is I've substituted in the G sine theta into there like that, okay? Hopefully that's pretty clear. All right, now we're in a position where we can actually start to compare our equations side by side. So I'm going to take the equation, the theoretical equation again, and underneath that I'm going to write down our equation, which was D is equal to 0.28 t squared plus, what was it, 0.0482. Is it actually a minus, not a plus? It's a minus. Okay, I'll change that. All right. Now you can solve this simultaneously. You can use a simultaneous equation, but we're going to choose an easier method, which is kind of the same thing, but a little bit easier. The first comparison I want you to notice, so we've got a DD. That's the same. That's easy. On the far right-hand side, I've got a plus C. I've got that. Does the theoretical equation have a plus C? It does, but the plus C is 0, right? It's 0. So straight away, we've got a difference between the theory and what you guys got, or what I got in my practical results. I've got an intercept of 0.0482, and I shouldn't have one. Now, what you're going to do later on is come up with some reasoning why you may have an intercept. Why is it that for a 0 distance, or sorry, for time equals 0, you've already got a distance? So that you've got to think about what that might be. It could be as simple as your timing is out. It could be that the ball was already rolling slightly, and it took you a bit of time to start timing. It could be the other way around. It could be that you started timing before the ball started rolling. Now, if you look at it, look at my intercept. How significant is that intercept in terms of a time? It's pretty small, eh? So in this kind of case here, where it's so tiny, it may actually be that you say that number is so small compared to the timings that actually it's insignificant. However, if you have a big number as an intercept, you're going to have to explain it somehow. And it's got to come down to your experiment, something that you've done or something that wasn't controlled or something like that. All right, that part's obvious. So we meant to have a plus 0. Okay, I could have added that in there. And we've got that, which shouldn't be there. All right, let's compare the last part of the equation. If I highlight the t squared, that one's got a t squared, that one's got a t squared. If we're making them the same, if we can compare them side by side, hopefully you guys can all see that a half G sine theta should be equal to what? 0.28. Okay? So if we can compare them side by side and matching all the symbols up, half g sine theta should, in theory, be equal to 0.28. 0.28 is your theoretical gradient, sorry, your experimental gradient, and the half g sine theta is the theoretical part of it. What we can do now is we can see how good your gradient is, your 0.28, by comparing it to something we know. And we all know g. Now, somewhere in the brief, they probably told us what g was. I can't remember what they did, but let's just say its g is 9.8.
We use sine theta.
Newtons per kilogram. Yeah, exactly. Absolutely. So we know that g should be, in theory, 9.81 newtons per kilogram. And we're going to use this little equation here to figure out what our g comes out to be based on our gradient of 0.28, which comes from our experimental data. So a little bit of rearranging here. You could try solver, but the solver doesn't always play the game with the trig. So what we're going to do is rearrange this. First of all, get rid of the half. So g sine theta. Divide by half on both sides, or multiply by 2 on both sides. 2 times 0.28. Next step, get rid of the sine theta. So I'm going to divide by sine theta on both sides. At this point, you need to substitute in your theta, the one that you measured. Okay. In my case, if I just scroll up and have a look here, my theta was 4.6 degrees. So I'm going to put that in. So g is going to be equal to 2 times 0.28 divided by the sine of, what did I say before? 4.6, was it? Degrees. Okay. All right. At this point, we calculate what that is. So I'll just do it now on this calculator here. Make sure your calculator's in degrees. That there's a bit of a gotcha, which can cause some problems. Okay. So actually, I'll do it on the screen instead. So with your calculator, you're going to want to go to the run mode, and you want to go to setup. At the moment, mine's in radians, so I'm going to change to degrees. I can now get out of that, and I'm going to go 2 times 0.28, and then I'm going to divide that by the sine of 4.6. Hold on a second, let's get rid of that. Too many sixes. And yep, that looks good. So 6.98 to two significant figures. Newtons per kilogram. All right, so that there is how you actually determine how close or how good your experiment is compared to theory. Straight away, I can see I've got a problem, right? Gravity should be 9.81, and I'm getting a gravity that's too low. Now, for excellence, your challenge now that you've done the theory, you've done the comparison to theory, your challenge is to actually come up with some good reasoning as to why your gravity is too low. And looking around, so from yesterday, every single one of you that I saw had a gravity too low. So the challenge is, how do we explain why it's too low? All right, I'm just going to pause the recording, or stop the recording, and break it up.